All chemical equilibria are dynamic, meaning that neither the forward nor the reverse reaction stops. Instead, the rate of the forward reaction is equal to the rate of the reverse reaction when the reaction is at equilibrium. Reactants are converted to products at the exact same rate that products are reconverted to reactants, so there is no apparent change in concentration of either reactants or products over time when a reaction is at equilibrium. A reaction at equilibrium can be shifted out of equilibrium. In other words, the forward and reverse reaction rates can be made no longer equal to one another. And this can occur by changes in pressure, changes in temperature, and addition or removal of a reactant or a product. We'll discuss that in more depth at the end of the chapter in a topic called Le Chatelier's principle. The mathematical relationship governing chemical equilibria was chemically derived, that is, derived based on experimental observation. The particular observation was that regardless of the initial concentration of the reactants, and you can see a variety of different conditions here, regardless of those initial concentrations, the ratio of the concentration of products to reactants, both raised to their stoichiometric coefficients, at equilibrium always had the same value as long as temperature was held constant. We call this ratio, products over reactants, the equilibrium constant expression. The composition of the equilibrium mixture always fits the same mathematical relationship shown on the previous slide. That mathematical relationship is called, again, the equilibrium constant expression. And its actual value, as we'll see on the next slide, is called the equilibrium constant. It's important to note that the equilibrium constant is constant only for a given chemical reaction at a specific temperature. It's not a constant like the ideal gas constant that always has a specific value. Now, the equilibrium constant expression often is written using molar concentrations, and that's why we put this little C here beside the K. Sometimes the C is omitted, and sometimes it's replaced with an EQ for equilibrium. Here I've written out the equilibrium constant expression for the reaction of A plus B going to C plus D, where the stoichiometric coefficients are little a, little b, little c, and little d respectively. We've written this equilibrium constant expression as the concentration at equilibrium, and it's very important to remember that you can only use equilibrium concentrations in an equilibrium constant expression. Those concentrations of the products at equilibrium over the reactants at equilibrium, with each individual species raised to its stoichiometric coefficient. Remember that we call this part, the actual mathematical fraction, the equilibrium constant expression, and the value of Kc itself, the equilibrium constant. The square brackets indicate molar concentrations, again giving us this little c here as a subscript.